Topic modeling. It's really warm here. La 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 la. La 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 la. Being patient, self-aiding inspiration. I'm so. Well, turn it on. Fuck. It's the time. So let's say topic modeling. Let's go topic modeling and ChatGPT forever. La 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 for and la la la. By the way, why don't I open the ChatGPT app? La 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 la. Quitty from my doubts. You ain't the same kind. Why doesn't it drop? Why doesn't it grow up? ChatGPT, and then we are going to ranking algorithm, and then we are going to fucking stupid searches. What is PCA? Okay, let's go over the paper. I learned some new techniques on how to do literature overview, and you go to the most recent paper in that topic, and they have introduction which covers the literature review. That's how you do it. I learned it from one of my students. Ha 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 ha. Who could have thought this? Ha ha. Okay. Oh, okay, we went to TF-IDF, and then let's bring the paper. Let's open this paper. Learning la 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 la. So clickbait, latent Dirichlet allocation, shen. Oh, Andrew Ng, Young, Wang, Michael Jordan, and David Emblay. So that's it, and then we said kind of they are like corner points of the whole space of all. We have documents, we have vocabulary, we have and what we define as a topic is not a title, but it is a distribution. And it's, what was that? Like, we had a sentence about being part vibe, part feeling, part science, and then we had I don't know, my dogs don't hate science. What else did we have? Let GPT label it. Why not? That's a good idea. Oh, we actually went over an example. Like, we have terms and documents. Like, one of our document is you start with a no, and then we had K topics. Decision. Oh, that was it. Part right, part science, part la la la. Was, what is the number of topics we want to consider? Number of topics we want to consider, K topics. And okay, I want to see the examples we had. And probably like finding centroids of those clusters. Centroids of those clusters are maybe the name of that topic, but it's not a good idea to choose the mode on. Okay, so, and all right, the other metric we TF-IDF was about how many times a term is used in one document may show that that is a critical word. But if the same word is used in all of your documents, it's probably showing that this is just the whole word, which means like it is in every, like is, am, are, the. But if it is football in one, okay. However, I feel it has kind of an intrinsic bias towards giving topic to each document and pushing your documents as, but it was just a metric. All right, let's not get serious on it. All right, score of omega, we give a score to a word, and probability of word given a topic times log of one level. All right, let's go over, okay, let's go over what we, and we decided not to read the paper first. We came up with another idea. La 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 la. So, okay, can you explain this paper? TF-IDF, latent semantic. We just need a metric that works well. Probably latex, latex, indexing, PLSI. So, topic distribution, theta D, generative process of LDA. Alright, I don't want to get into it right now. And then we want to say, fuck that. I said, fuck that. Tell me what the problem of topic modeling is, and I want to come up with a model for itself, myself. Alright. Then we have like 3 documents. I love football. The team played a great game. The coach was happy. Sport, maybe. The government passed a new policy. The president gave a speech. Politics, probably. My favorite player scored 2 goals. It was a thrilling match. Again, sport, probably. But for formally, what you want the model to do is, let we have D documents, total number. V is the vocabulary size, and K is the number of topic you pick. So vocabulary size we are given, number of documents we are given, number of topics we have to choose, and then for each topic a distribution over those words for the document D. Distribution topic is So each topic, which is 5k number of topics, is a distribution over words, and for each document, and you're saying document is mix of these topics, so it's kind of distribution. Okay. So it is actually a convex combination of those topics. So I was right that I said 5Ks are kind of the extreme points of this distribution over vocabulary. Comes from generated from that topic word distribute. So it's very interesting because you can have all these extremes, and we have like kind of convex combination. Most of us are not the extremes. We are just I don't know if it is even good to be an extreme. And then if you're balanced, you're somewhere in the middle in this convex cone, and we have some attributes of each of these extreme points or vertices. So we have room to go toward each of these extremes. Where you come from, where you come in. LDA is one way to do this, but you want to come up with your own model. Hell yeah. Let's go. Here are some angles you could explore. Simpler model. Cluster words, then docs. Topic evolution over time. Neural model, interactive modeling. You went too far early. I don't have intuition over why topics are treated as distribution over words. Alright, I was thinking last time topics may actually be distribution over documents. Yes, I do. Let's try down your real intuition. Let me see what's my next. What about assigning each word a distribution that say belong to each topic? We don't do that. Okay. So we say we have K topics, and this actually that makes a lot of sense. Like a word like football, how often it is in sport, how often it is in news, how often it is in cooking, politics. Sorry. And then you can say, I didn't bring water. And then we can say, so that's my approach, what I was thinking about. And they are saying, no, actually we have these topics, and the probability of each word showing up in this topic is this. Is there a Bayesian rule that can connect these two? Bayesian rule that can connect these two? Bayesian rule. So if the probability of words showing up belonging to this topic so it's a distribution over topics, right? So we have, what I'm saying is probability of word W belong to this topic T or phi 5k. So it's a, how many is it? It's like P1 to Pk. But the way they are modeling it is probability of this word. Oh, they are doing the other thing. They are giving a probability distribution for each document. This document can be, okay, I don't like that. So yeah, that makes more sense actually. So I think at the end of the day, we have some room here. That's what it is. That we have some room, and they decided to go, yeah, let's give each topic a distribution. And words are not distributions over topics, but topics are distribution over words. So that's it. My model was words are distributions over topic, and they were like topic are distribution over words. And then I wanted to say, then we wanna, at the end of the day, what matters to us is that these are, I think, the designer's choice. If maybe both of them can work, but what is important to us at the end of the day is probability of this document belonging to this topic K. This is something that our consumer wants to use. The consumer wants to give us document until he expects us to tell them what topic it belongs to. All right. Then the rest of the thing are we design our model. So we have some create room for creativity on how to do it. So if we are going with the cool paper model, we can say, for example, probability of this topic belonging to this topic is pi of each word in the document belonging in it. I don't know, I'm just going with something, right? 5k. And I say this is it. Definitely needs normalization or something. Other thing is that saying, alright, what happens if I wanna say go with my model? Probability of D depending on the topic K is that pi of words in that. Oh, words now are each one. Yeah, I can say phi k or like phi k maybe. Phi w of k. I can say that too. Yeah, I think at the end of the day it's about the matrix view of this, like each word and each topic, this pair has a probability. They are saying we can sum over the rows, I'm saying we can sum over the columns to get one. What if the matrix is doubly stochastic? Fuck that. Alright. That's actually a very natural and super powerful way to think about it. Let's break it down. Like game might be 70% sport, 30%. That's 100% value, and you are not alone. This leads to some super interesting models. Real intuition, word ambiguity. Each word distribution over topics makes some total sense. Let you say the meaning of this word depends on the context. Formal vibes. You are proposing a model where, they use psi. For each word for W, assign a vector psi W over topics. Then for document, you sample words W. Is kind inverse LDA. So okay, we were actually legit. Each topic K has a word distribution for K words are generated. You could build a model like this. Oh, now they are defining new parameters like theta D. Documents topic mixture. Each document is a bag of n words, and then like it is the average of psi of those. doesn't make sense. Oh, okay. By the way, you can look at the Word as by itself as a document too, and LDA should say what is the topic of this. So could be a cool model if you're working with small data, fewer tokens to estimate per token topics. You want a fast, shallow, and interpretable topic model, then to try embedded driven or pre-trained prior word to vec. Who and how chooses the number of topics? Okay, it was that famous sentence, and then we said and then who chooses the topic as the part of the vocabulary. I see. Okay, okay. Then we had all those use ChatGPT, manual labeling. Okay, what is this? Heuristic. What is TF-IDF? Okay, so TF-IDF was not a main thing. Okay, let's get back to paper now. I got an important email. jump into paper. Time to jump, time to jump. I'm very happy I have Munzer as my supervisor. I was listening to him yesterday on YouTube. Dude, when Munzer talks, you wanna always listen, bro. Talks so nice. Fuck it, this is warm. Okay, let's jump into paper, but first from a ChatGPT point of view. Let's jump into paper now. Yes, let's jump in. We are talking about the LDA paper by Blay, Ng, and Jordan, 2003, 22 years ago, which you uploaded earlier. You already, why do you think I paused on 22? It could have different reasons behind it, because either it can be, I'm not sure which year we are, 25 or 26, and I say, took me some time to find 22, which is the reason. Or it could be, I couldn't do 25 minus 3. Never judge a person, alright? You don't have enough data, which you uploaded. You've already, so you already got some great instincts. I have the best instincts about topic modeling. So let's go through it from your perspective and make sure we highlight why each step is there. Big picture first. What's the problem? Oof, oof, oof. Yeah, we have a big pile of documents. I think this is a good paper, but I'm also gonna read one more paper about topic modeling, which is the most recent one. And we are going over the introduction, and it is beautiful. What's the problem? We have a big pile of documents. Alright. Pile of documents, not words. Each document is a big pile of words. So, text data, we don't know what they're about, and no labels. Okay. And we want to automatically discover the hidden topics in these documents. Hidden topics in these documents. But we need to know the number of the documents. What does LDA do? It builds a probabilistic model that assumes each document is a mixture of topics. So this is a big assumption. This is part of the art of the research they did. Mixture of topics. The design part. Oh, do you remember the talk we had with Amin that we have design problems and optimization is kind of inverse design? So this is the part of design part. It builds a probabilistic model that assumes assumptions. Assumptions are beautiful. Each document is a mixture of topics, convex combination of those topics. So each document by itself is a distribution over words. That's what a document is. So we have, so that's what we have. We have documents which are distribution over words, right? So we have like D document. We have D, which are, what are they? I want to say 3, we use 5, we don't want to use psi. Let's say F. We have F1 to FD. They are all distributions, meaning F1 is sigma A1 K, small k, k from 1 to k, big K, A1K, phi K, right? And sigma A1 should phi, each phi is alright. So F1 of W is phi k of W, sum over W should 1, sum over W should 1, and then it's, yeah, sigma AIK should be 1. What's up? Alright, fuck this. Okay, so sigma AIK for each AI. Yeah, fuck. Oh, yeah. So for each D actually, because we are counting documents, sigma ADK should be 1, sum over D. Not sum is over K. ADK for each D should sigma ADK should be 1. By the way, I don't want to get into math. Honestly, we don't. We just want to see what's up there. ADK, because this model, as I told, can change in another paper. Let's get the big picture. Fuck that. And yes, we don't want to get into math. And then F1 is just extreme part. Okay, the part I want to get in, I don't want to get into math of this. I want to get into math of mine. So we have D. That's the problem. I wanna abstract away all this bullshit about words and documents. So we have D um, distributions, and we want to find K. That's what we want. We have D distributions, and we want to find K distributions that cover those D distribution as the extreme point. All right. So actually, we want to find the convex hull. That's what we want to find. We want to find, like throwing a string around. That's what we want to do. Let me share my screen actually. So that's it, right? We have, it says documents like F1, F2, J1, J2, and then we have a lot of dots. These are our documents, which are distribution over, and we have this FD, for example, last one, and there are some here, there's some here, there's some here. Oh, sorry. Um, We are creating content here and people are February. Then I have March 6. Then I have March 13 and April 10. Yes, that's true. Alright, okay, what is it? So we have these are a bunch of documents we have, their distribution over words, whatever. What we want to do is finding um, K points that we put on this plane. Here we have like plane. Okay. Whatever this distribution belongs in. Okay. So that like 1, 2, 3, 4, 5. The convex, is it called convex hull? Yeah, convex hull of these points include our documents. Then anything inside this convex hull can be said as a mixture of these five. You may say, well, I can have 6, right? Another one can be a 6, like this, 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 and then you can say this. And then one famous problem is that if you get the intersection of all these convex hulls, you will have the minimal convex hull, which is probably this color. Which is the minimum, in a sense, minimum, because it is unique actually. So of all these convex hulls that include all of our documents. So some of our documents actually will be the extreme point. Is that true? Minimum convex hull, what is it? Minimum, is it called minimum convex hull? Convex hull. Alright, so we can have this, and some of the extreme points will be our current documents, and other current documents can be like this, which has like 1, 2, 3, 4, 5, 6, 7 edges. I don't know what is the problem here now. Is it like finding the minimum convex hull? Because if you choose it bigger, then you will have more distributions allowed. But you can see that if I wanna get minimum convex hull, I may end up having so many topics, right? Having a lot of topics. If I want the minimum convex hull, I can get 7 topics here, right? That's actually a nice question. I can get 7 topics. So let's assume we are looking at an octagon. Right? Let's assume these are our documents, right? So randomly, well, I designed them. They are actually the only convex hull, like the minimum convex hull will be actually our documents have to be on the minimum convex hull. There is no convex, smaller convex set that contains all of them, and they should be on the extreme points, right? So this is it, but this way we will end up having 8 topics. That may sound too many topics. You are saying actually each document is a topic, which sounds very granular view. What if you want to have a more summarized version, right? What if you want to say, yo, I want a document which is, you tell me. I don't know. I want to have 4 topics. I don't want to make it too complicated. I want to have just 4 topics. Then you should find the convex hull that is 4 topics. Like you need to find 4, and probably what is the minimum 4 topic? I don't know why am I optimizing on this minimum, but it's just some other notion I learned. So what is the minimum for extreme points that we can set that? Alright, you can set your points here, guys, by the way. You can choose your set so big, like here, 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 that it contains all of your documents. You can set it here, right? You want to make the square. So choosing these topics doesn't sound to be unique, by the way. Like this is a 4 topic precision. Another 4 topic one can be this one actually. They are pretty much the same size. So and you can say what is, like if I want to choose 3 topics, what is the smallest? Here we should use minimal actually, not minimum, but minimal maybe is the choice. What is like the minimal triangle we can put on this? That's actually a good question. I'm interested in this. So let me ask ChatGPT by the way. So that's a good question. I haven't studied this far on convex sets. So if I have this right octagon and right, what's up? So if I have this octagon, what is the minimal triangle I can put on it? So is that it? Then every triangle I want to pick, that may be 1, right? It's goes all the way here and just hits it here. The other one can be this. Is it minimal in a sense? Like it's covering an edge? Honestly, I don't know. What is minimal actually? What is the definition of minimal? Minimum in area? That's an interesting question. Alright, so let's go. So, alright, I'm not asking, I'm not jumping into the paper yet. If document, it seems topics are convex hull for the documents. Alright, yes. Wow, dude, that's it. That's when your mathematics is so good and you know the fundamentals and you know go fucking code yourself, motherfucker. Alright, you just nailed one of the most beautiful geometric interpretation of topic modeling. I haven't looked at the paper yet. Topics in LDA form a convex code that contains all the document in word space. Let's dig into that. Single it as each topic beta k is a point. So they're saying it was phi k in the v-dimensional word probability space simplex. This is over word. So with k topics, you've got k dimensional space. This points span a k minus 1 dimensional simplex. Now each document is a mixture of those k. So the document is placed at this, which means the document convex hull. In a nutshell, the topic simplex lives in a high dimension of the document. Topics, corners, documents, interior points. This is what makes LDA better than hard clustering. Mixture of unigrams. Each doc picks one topic. It lies at the one corner. So they are saying doc picks one topic. Oh, okay. Each doc is a weighted mix. Oh, okay, that's simpler. This flexibility while so 1, 2 visualize it. If topics are a corner or corners, that should their convex combination should cover the dots. Then we have a lot of room on choosing them. What extra metric narrows down our decision should they cover a minimal space or be a convex hull. I don't know if minimum convex hull. I think convex hull is actually minimum. Convex hull should be the convex hull. Or if it is not this, it means we have some new information. It's not just geometry. Through the math now, you're asking exactly the right question. Let's tackle it carefully. What you just said. Topics are corners, documents are inside the convex hull of topics. There are many ways to choose topics so that their convex hull covers the documents. What extra principle narrows down which topics we choose? What does LDA actually do? LDA does not choose topics by saying just make sure every doc is inside the hull. That would be too loose. Alright, yes. Instead, it adds more probabilistic structure. So we need more to narrow down. Smooth documents have sparse, smooth distribution. Okay. What does smooth distribution mean, by the way? Sparse makes sense. Smooth, I don't know. Over topics, controlled by if it wants the topics and the topic mixture to explain the document with high probability. Okay, it's another requirement that topics and topic mixture documents with high probability. If we choose these topics, these are like 5 topics, each document should have a high probability in one of them. Something actually related, by the way, let's not forget our own work that we are choosing, like there are 2 categories, then we want relevance of one item belonging to one category be very high and in others be very low. It tries to maximize likelihood, observed word under the model mixture proportion, topic word distribution. It's not about minimal convex hull model, it's about good generative probability. Should look natural if generated by top. I see. Makes sense. Alright. Extra constraints implicitly. LDA pushes the model to prefer topics that make documents easy to generate. Each document can be explained by picking topics and then picking words. What? I agree with the word push. I think it's like documents will be topics in a sense. Allow sparsity if needed by tuning alpha Dirichlet prior. You can make documents be a mixture of just a few topics rather than all of them, avoiding out overfitting. It leads to a different kind of model. In some alternative models, anchor word methods, sparse coding, they try to find topics that span the document, small simple hull as possible. A volume or entropy perspective. LDA does not minimize it. So I think we are good with geometry in total right now. If you don't want to take geometry to extreme, if you want a minimal convex hull approach, alright. Perfect. Now let's get back to the paper. Through my eyes. Wow, ChatGPT is so arrogant. Introduction. Motivation represents text corpora in a lower dimensional way while preserving important statistical structure. Previous methods, 2F, IDF, LSI, either miss semantic structure or lack a proper probabilistic model. Professor Pablo Perillo, PLSI was better but has flaws. Why are you so flawed? No full generative model for new document. Too many parameters over. We need a better model, LDA. Weather got better. Uh, Guys, I need some water. So I will get a pause and I will come back. Okay, took some time, but good point was that I reminded myself that I don't want to get into the math. So Mirishland, I wanna know as least as possible. I wanna know the big picture, what's going on. I don't wanna prove the theorems. I don't wanna get fucking bullshit in my head. Applied mathematics. Fuck applied mathematics. You know, fucking, I hate this term. This is the disgusting word ever existed. Disgusting. You have mathematics. Fuck you, by the way. I don't speak to you. I speak for myself. I want mathematics. I don't want mathematics anymore. But if anything, mathematics is beautiful for itself. It is not beautiful for application. That's my take. That's my take. Clear. If it has application, nice. But I'm not changing my whole character and say, oh, now I look where I can use math as application. I like mathematics because it is beautiful, because it is engaging. You feel you are smart when you solve a problem. You enjoy. That's it. The other thing are other thing. I think if you solve an applied problem, you will enjoy that as well. But you give yourself this identity that I have to turn mathematics into something applied. I don't like that. Alright, awesome. Let's steer right back to the LDA paper. You already understand the geometric feature super well now. Now let's reframe the paper's flow based on that understanding. You will see the structure even more clearly. LDA introduction motivation represent text corporation in a lower dimensional way while preserving important statistical structure. So we are caring about semantics or lack proper proposal. PLSI was better. Flaws. I don't want to compare these models, to be honest. I just want to know what is not even LDA. What is topic modeling? What is the main problem? We need a better model. LDA, vocabulary size, M number of documents, number of words in document D. Each document D sequence of words, WD1 to WTN, model latent, directional allocate. So this is the math part that I probably don't want to get involved with. So let's be as minimal as possible. Document is a mixture of topics. Distribution over words, generative process for document D. Generative process for document D. Process for document D. Yeah, why should I fucking watch YouTube? I hate myself, you know. Sometimes this curiosity, I know, that's like seeking drama. Alright, generative, not. Yeah, I can do it on Sunday for 1 hour, that's it. Then the rest of the week we are working. Focus on ourselves. Who are ourselves? It's just me here. Generative process for document D. You guys, you are here too. Theta D, Dirichlet alpha. Okay, this is a parameter. These are, what is theta D? Theta D documents topic. Oh, theta D is the vector of those weights. For each word, sample topic assignment. for each word we have a topic assignment. That's actually interesting, so it is closer to what I said. And sample word WDN, multinomial beta ZDN. Alright, I don't know, get these terms. But the joint distribution of hidden and observed variables, theta, z, and. Alright, let's go. What is draw the concept? What is theta? Theta d and LDA. Theta is the topic mixture of document. This is a vector of length k. Okay, sum to 1. Yeah, because alpha, I said alpha, alright. So it is the weights, alright. Lives inside k minus 1 simplex. The entire are non-negative, sum to 1. Each number negative k. What fraction of document is a topic k? K is 3, topic 1 sport, politics, and food. For a specific document D, theta d. Sports and politics and 10% food. What can be it? Let's say a sentence that is 70% sport, 20% politics, and 10% food. So sport is like football. David Beckham plays in Manchester United. And if I want to add 20% politics to it, David Beckham plays in Manchester United and he voted, right? This is 20% politics. And 10% food. David Beckham plays for Manchester United and he voted while eating French fries, whatever. So when generating the document, each word randomly choose a topic or then why Dirichlet? Alpha is the parameter of the Dirichlet prior. Alpha controls how sparse or uniform the topic mixtures are. Small alpha that can mostly use few topics. Alright, okay, what is Dirichlet? I don't know. So it's something. Are you very ping? Alpha is the parameter of Dirichlet and what controls how sparse or uniform the topic mixtures are. Mostly use few topics. Large alpha means many topics at once. So how narrow the conversation? Dense mixture and sparse mixture. Sparse mixture means you're almost on one, focused on one topic. Dense mixture means you are a combination of all. You can think of alpha as how many topics per document. No. So can you plot and give formula for Dirichlet? Alright, by the way, let's not get out of the main path because okay, well, next questions are these. For each word. Alright. Ooh, that's so beautiful. What is it? Alpha is 1, 1, 1, and then we have alpha. Oh, okay. Dense and sparse. Dense and sparse are also beautiful. Version of samples. So alpha is actually a vector, not. That's interesting. Alright, then what is the other is? Let's get back to the model. Position and several topic word. Topic assignment ZDN. These document N is the word and multinomial theta D. Randomly pick one of the topics according to the document's topic distribution. Sample the word multinomial. Having chosen a topic, you now pick a word according to that topic word distribution. In each word in the document. First, what topic am I thinking about? Sample from theta. Given this topic, which word fits? What is beta? How people write. Then switch to politics. Okay. Mathematical details. Sampling topic set. Theta is a vector such game. Is a one hot vector that says which topic document D word N 1 or 0 is the probability of choosing topic. K is theta dk. Okay, yeah. Multinomial over topics means pick one topic per word, the chance of picking. What is beta? Sampling the word WD. Topic K has its own word distribution. But it was okay, that was FICA, that was not beta. Alright. There are over vocabulary, so I didn't. Micro example. Alright, let's go over example. Examples are the best at getting intuition. Suppose three topics: sports, politics, and food. Food, vocabulary, goal, election, erection, burger. And so that's a good sport. Document topics, theta is this. Theta of D is this. What about theta of the word? We had theta dn, okay. Topic word distribution, sports, beta of sports. Okay, these are the phi or phi's. Now they are phi. Betas. Beta of sports is so goal. Okay, what are betas of distribution? Distributions over words. So betas are distribution over goal, election, and burger. So if you go sports, 90% of time goal is the topic word. Election 5% of the time show up. Burger 5% of the time. Politics, election shows up high, right? And food, burger shows up high. Alright, sounds good. Now generating a word sample topic. Okay, now we want to generate the word. We first choose the topic, then we choose a word. So 0.6 we choose sport, and 0.9 we choose goal, so it's like 0.54%. Alright. ZDN. With topic produce the words. Alright, so I see. So they, at the end of the day, connected the topic and the word. In my model, it was reverse. So what is the probability of this word belonging to this topic is topic to the word. Um, um, sorry, just stupid thoughts. Get make myself distracted. That's stupid. So how do you do that? You get beta times theta will become your z, and that's why inference is needed to figure out. And given only the word, what the topics and diversion. Okay. No, honestly, I don't want to get to the likelihood, and let's go. Something fell before we continue either way. Oh. So let's go into the paper. We describe latent Dirichlet allocation (LDA), a generative probabilistic model for a collection of discrete data such as text corpora. LDA is a 3D. Can you read it to me? Alright, let's go fast. Skip. 3D region model, which is type of collection. Set of time. Text, the context of text model. Explicit representation of the present efficient approximate inference with some variation rather than in your algorithm. So this is about their algorithm and bullshit. For empirical based parameters, that's the I wanna find the problem. I'm not interested right now at least that much in their solution or their method. So it's called document modeling, text classification, collaborative filtering. Collaborative filtering also was related to recommender systems, comparing to a mixture of unigrams model and probabilistic LSI model. Introduction. The problem of modeling text corpora and other collection of discrete data. Jesus. Alright. In this paper, we consider the problem of modeling text corpora and other collection of discrete data. What is text corpora? What is corpora? Is like corpus, I think. What does it mean though? A collection of written text, especially the entire works of a particular author or body of writing on a particular subject. Alright, corpus. And the plural is corpora. Alright, and okay, they say introduction is the most interesting part of the paper. Always sleep in it, so let the fucking ChatGPT read it for me. By the way, is there any question we can ask here from our collaborators? Well, we are not deep inside yet, so. Dude, come on. Why does it take so long time? So can you read it for me?
Sure. Here's the text you asked me to repeat. In this paper, we consider the problem of modeling text corpora and other collections of discrete data. The goal is to find short descriptions of the members of a collection that enable efficient processing of large collections while preserving the essential statistical relationships that are useful for basic tasks, such as classification, novelty detection, summarization, and similarity and relevance judgments. Significant progress has been made on this problem by researchers in the field of information retrieval, IR, Beza Yates and Ribeiro Neto, 1999. The basic methodology proposed by IR researchers for text corpora, a methodology successfully deployed in modern internet search engines, reduces each document in the corpus to a vector of real numbers, each of which represents ratios of counts. In the popular TF-IDF scheme, Salton and McGill, 1983, a basic vocabulary of words or terms is chosen, and for each document in the corpus, a count is formed of the number of occurrences of each word. After suitable normalization, this term frequency count is compared to an inverse document frequency count, which measures the number of occurrences of a word in the entire corpus, generally on a log scale, and again suitably normalized. The end result is a term by document matrix, X, whose columns contain the TF-IDF values for each of the documents in the corpus. Thus, the TF-IDF scheme reduces documents of arbitrary length to fixed-length lists of numbers. While the TF-IDF reduction has some appealing features, notably in its basic identification of sets of words that are discriminative for documents in the collection, the approach also provides a relatively small amount of reduction in description length and reveals little in the way of inter- or intra-document statistical structure. To address these shortcomings, IR researchers have proposed several other dimensionality reduction techniques, most notably latent semantic indexing, LSI, Deerwester et al., 1990. LSI uses a singular value decomposition of the X matrix to identify a linear subspace in the space of TF-IDF features that captures most of the variance in the collection. This approach can achieve significant compression in large collections. Furthermore, Deerwester et al. argue that the derived features of LSI, which are linear combinations of the original TF-IDEF features, can capture some aspects of basic linguistic notions such as synonymy and polysemy. To substantiate the claims regarding LSI and to study its relative strengths and weaknesses, it is useful to develop a generative probabilistic model of text corpora and to study the ability of LSI to recover aspects of the generative model from data. Papadimitriou et al., 1998. Given a generative model of text, however, it is not clear why one should adopt the LSI methodology. One can attempt to proceed more directly, fitting the model to data using maximum likelihood or Bayesian methods. A significant step forward in this regard was made by Hoffman, 1999, who presented the probabilistic LSI, PLSI model, also known as the aspect model, as an alternative to LSI. The PLSI approach, which we describe in detail in section 4.3, models each word in a document as a sample from a mixture model, where the mixture components are multinomial random variables that can be viewed as representations of topics. Thus, each word is generated from a single topic, and different words in a document may be generated from different topics. Each document is represented as a list of mixing proportions for these mixture components, and thereby reduced to a probability distribution on a fixed set of topics. This distribution is the reduced description associated with the document. While Hoffman's work is a useful step toward probabilistic modeling of text, it is incomplete in that it provides no probabilistic model at the level of documents. In PLSI, each document is represented as a list of numbers, the mixing proportions for topics, and there is no generative probabilistic model for these numbers. This leads to several problems. One, the number of parameters in the model grows linearly with the size of the corpus, which leads to serious problems with overfitting. And two, it is not clear how to assign probability to a document outside of the training set. To see how to proceed beyond PLSI, let us consider the fundamental probabilistic assumptions underlying the class of dimensionality reduction methods that includes LSI and PLSI. All of these methods are based on the bag of words assumption that the order of words in a document can be neglected. In the language of probability theory, this is an assumption of exchangeability for the words in a document, Aldous, 1985. Moreover, although less often stated formally, these methods also assume that documents are exchangeable. The specific ordering of the documents in a corpus can also be neglected. A classic representation theorem, due to Definetti, 1990, establishes that any collection of exchangeable random variables has a representation as a mixture distribution. In general, an infinite mixture. Thus, if we wish to consider exchangeable representations for documents and words, we need to consider mixture models that capture the exchangeability of both words and documents. This line of thinking leads to the latent Dirichlet allocation, LDA, model that we present in the current paper. It is important to emphasize that an assumption of exchangeability is not equivalent to an assumption that the random variables are independent and identically distributed. Rather, exchangeability essentially can be interpreted as meaning conditionally independent and identically distributed, where the conditioning is with respect to an underlying latent parameter of a probability distribution. Conditionally, the joint distribution of the random variables is simple and factored while marginally over the latent parameter. The joint distribution can be quite complex. Thus, while an assumption of exchangeability is clearly a major simplifying assumption in the domain of text modeling, and its principal justification is that it leads to methods that are computationally efficient, the exchangeability assumptions do not necessarily lead to methods that are restricted to simple frequency counts or linear operations. We aim to demonstrate in the current paper that by taking the Definetti theorem seriously, we can capture significant intra-document statistical structure via the mixing distribution. It is also worth noting that there are a large number of generalizations of the basic notion of exchangeability, including various forms of partial exchangeability, and that representation theorems are available for these cases as well. Diaconis, 1988. Thus, while the work that we discuss in the current paper focuses on simple bag of words models, which lead to mixture distributions for single words, unigrams, our methods are also applicable to richer models that involve mixtures for larger structural units, such as n-grams or paragraphs. The paper is organized as follows. In Section 2, we introduce basic notation and terminology. The LDA model is presented in Section 3 and is compared to related latent variable models in Section 4. We discuss inference and parameter estimation for LDA in Section 5. An illustrative example of fitting LDA to data is provided in Section 6. Empirical results in text modeling, text classification, and collaborative filtering are presented in Section 7. Finally, Section 8 presents our conclusions. Let me know if you want me.
You know what? I think. Wait, why can't we have the. I don't want to dictate, but I wanna talk. It doesn't have. It has. Anyways, so first of all, thanks they read it to me because I just noticed it is much faster. Fuck that. I didn't. If I read it, I used to go in every detail and I was like thinking about each sentence. Fuck that. So it is this and then. Oh, okay. So they are using, fuck you, ChatGPT. They are using W as document and corpus as D, while ChatGPT was Word as document, Word and document as. N Poisson, theta, Dirichlet, ratio, and words like ChatGPT can fuck you up too. Then topics are Zn, word Wn. Then the word is the okay. So this is the Dirichlet. The joint distribution of a topic mixture theta, a set of n topics. Fucking, he said k topics, and I think n z, and a set of n words. Okay, so this is the problem with the paper. Is given by probability theta, z, and w given alpha. What is beta? Oh, beta is the probability of each topics are beta. Theta given alpha. Alright, Dirichlet, n1 to n. This word belongs to this theta. Probability of this word showing. What was Zn again? Zn is topics. So beta, what the fuck is beta? If Z is... Let's ask ChatGPT. What's the difference of beta and Zn? Theta document those weights. Zn is topic assignment for. Okay. So each word has a. Okay, Zn is computed based on the fucking beta and theta. Yes. Wn, the actual word position, n. Theta. Okay. Alpha, theta, and beta. So we have alpha and beta, which are extrinsic. Theta is generated based on alpha, which is kind of intrinsic. Yes. Then you have Z based on theta. Amen. Okay, Z is one hot. It's like this word belongs to this topic or not. So these are the then you compute the probability of a word, probability of document, and you have all of them. Exchangeability. Find a set of random variables z1 to n is said to be exchangeable if the joint distribution is invariant to permutation. Beautiful. So random variables. So if you are inside the document and you change the order of the words, is it going to be the same document? Or your algorithm will decide it is the same algorithm? Or if you want to say in our example, we have this ranking, the users clicked on it, and based on that we say that, alright, this item belongs to this category and the other item. If we change the order of the problem because of the bias of the ranking, can we say that? Probably we cannot say it's exchangeable. By the way, what was this? It says Definity. What was that math problem, that product of integrate over? What is the name of the theorem? Is it Foti? No. I don't know. Fotas theorem that talks about the integral over a product space and breaks it down into product on each space. Product of integral on each space.
You're thinking of Fubini's theorem. It states that if you have an
Fubini's. Alright, so it's another person. That is represented state that the joint distribution of infinite exchange of sequence of random is okay. The Finiti's representation theorem states that the joint distribution of an infinitely that's very beautiful, exchangeable sequence of random variables is as if a random parameter were drawn from some its IID. Then random variable where IID conditioned on the parameter. We assume that words are generated by topics, alright, by fixed condition, and that those topics are infinitely exchangeable within a by definition. The probability of a sequence of words and topics must therefore have the form. So it's all product. While it was previous. Oh fuck, dude. Continuous mixture of unigrams. Figure 2, an example density on unigram distribution. Relationship with other latent variable models. Alright, these are math. Okay, they also have a geometric interpretation. So we have other topic modeling methods as well. LDA is only one, that's why I don't want to get into math a lot. And they are comparing them here. Like unigram, mixture of unigrams, PLSI and LDA. So we have a distribution over word distribution. Can be viewed as a point on view. So they all share the thing that what is a topic should be. So let's forget the details. We have some documents. I'm gonna say what topic or category they belong. How is it similar to our model? You wanna say how many categories? Let's assume we assume that we know the number of categories. What we have, what we can observe. And how do we have those phi's, by the way? Oh, we are learning, we are going to learn them. The same is in our case. Yeah, we were learning ours. And Okay, they have an example. An example article from the AP Corpus. Each color codes a different factor from which the word is putatively generated. So arts, we have new film, show, music, movie, play, musical, best actor, first York, opera, theater, actress, love. From budget, we have million, tax, program, budget, billion, federal, year, spending, new, state. So those are hidden. I see. Okay, children. And then we have perplexity, number of topics. You can see the number of topics increases, perplexity decreases. I think perplexity is a good thing, isn't it? So you don't want to have a lot of, even for LDA, they have a local, yeah, they have a maximum of 20. And then we have perplexity versus number of topics. Again, another thing. Oh, two data sets. Let's go to the document classification. Let's repeat the next. Why isn't ChatGPT desktop as good as ChatGPT on phone? Alright, so that's it.
Here's the full passage you asked me to repeat. In the text classification problem, we wish to classify a document into two or more mutually exclusive classes. As in any classification problem, we may wish to consider generative approaches or discriminative approaches. In particular, by using one LDA module for each class, we obtain a generative model for classification. It is also of interest to use LDA in the discriminative framework.
What is generative and what is discriminative? Oh, okay. That's a good question. Alright, why can't you read this again? That's so fucked up. Let me access it here.
Here's the full passage you asked me to repeat. In the text classification problem, we wish to classify a document into two or more mutually exclusive classes. As in any classification problem, we may wish to consider generative approaches or discriminative approaches. In particular, by using one LDA module for each class, we obtain a generative model for classification. It is also of interest to use LDA in the discriminative framework, and this is our focus in this section. A challenging aspect of the document classification problem is the choice of features. Treating individual words as features yields a rich but very large feature set. Joachim's, 1999. One way to reduce this feature set is to use an LDA model for dimensionality reduction. In particular, LDA reduces any document to a fixed set of real-valued features, the posterior Dirichlet parameters gamma W, associated with the document. It is of interest to see how much discriminatory information we lose in reducing the document description to these parameters. We conducted 2 binary classification experiments using the Reuters 21578 dataset. The dataset contains 8,000 documents and 15,818 words. In these experiments, we estimated the parameters of an LDA model on all the documents without reference to their true class label. We then trained a support vector machine, SVM, on the low-dimensional representations provided by LDA and compared this SVM to an SVM trained on all the word features. Using the SVM Lite software package, Joachim's 1999, we compared an SVM trained on all the word features with those trained on features induced by a 50-topic LDA model. Note that we reduced the feature space by 99.6% in this case. Let me know if you'd like a summary. Paraphrase.
Fuck up, I didn't understand anything. Alright, figure 10 classification results on 2 binary classification problems. So it means 2 topics, right? LDA is better than word features, accuracy, and then some of the proportion of the other one. Word features is better sometimes. Perplexity, predictive perplexity. Jeez. Okay. 2003 they were talking about perplexity. Now we have OpenAI. Alright, then they have collaborative filtering, and then I want to read the discussion, to be honest. I don't want to. Yeah, I'm happy I didn't get into the details. Thanks, ChatGPT, you saved me. And alright, let's go over what is the difference between generative approach and discriminative approach. Maybe that's a nugget of knowledge. Awesome question, first of all. This is one of those core ML distinction that completely changed how you think about. Wow, it's going to blow our mind. All right, break it down simply and clearly. Generative versus discriminative models. 2 different philosophies. Wow. Okay, we are getting philosophical. I have no idea why do we have these terms related to ML? What are we generating? What are we discriminating? I cannot connect the dots. Let's model how the data was generated. You try to learn the joint probability distribution. X and Y. Y are the label, X are the data, like the features. I want to see the P of X and Y. I see. Generative approach says, let's see how the data was generated. You try to learn the joint probability distribution. Or more commonly, P of X given Y, which is the likelihood given each class. Oh, Y are the classes. Yes, alright, I agree. Y's are the classes. Then you can use Bayes' rule to compute what is the range of this class given the features we observe, and this is it. Example, naive Bayes, LDA for classification. Hidden Markov models, Gaussian mixture models, use case useful when you want to generate synthetic data. You care about understanding how features behave for each class. you have missing data or unsupervised structure. So it's unsupervised. Well, in unsupervised we have why. Now let's go discriminative approach. By the way, for generative approach, it's using some like things like DNA emoji, but for discriminative approach, it's like using swords against each. Let's go straight for the boundary between classes. Probability of y given x. Conditional probability y given x, or even just the decision boundary without the threshold. Modeling problem. Logistic regression, support vector machine, neural networks, random forest impact. Useful when you only care about accurate classification. You don't need to model or understand the underlying data generation. Analogy. Imagine you're okay. That's a good. I love the analogy time because imagine you are trying to classify emails as a spam or not spam. So a generative model will say, where are these spams coming from? Yeah. And discriminative model says, what's the difference between a generative model tries to model how spam emails are written. Okay, and how non-spam emails are written. It's like trying to understand how each group writes. Okay, a discriminative model just look at a bunch of label examples and says, let's find the sharpest line that separates spam from none. Okay, that was, I got it, but I don't know how, like, can you go deeper on your example? Probably, so discriminative guess says P of y given x, generative says P of x, it's like max MAP and ML. Whichever is the decision boundary can handle missing data or labeled data. Is it? Like the difference of MAP and ML. Oh yes, you are so close to another terminology, but let's clarify the relationship. Generative versus discriminative is about what you model, the joint versus conditionals. ML is about how you estimate parameters, using priors or not. Same thing, but they are both accessed in the ML. Okay. So, alright. Oh, we have generative ML, naive phase, alright. We have generative MAP, we have discriminative. No, yes. Can you go deeper on your spam example? I'm not understood. Alright, we are learning about machine learning as well. That's really good. I don't wanna put the meat of my studies on machine learning. I wanna learn it as not minimal, but whenever it is necessary. Absolutely. Let's zoom in on the spam classification example and go step by step comparing how generative and discriminative model approach it. Classify email as a spam or not. We are given a data set of emails, each labeled spam is 1, not a spam is 0, so they are labeled. Each email is represented as a vector of features x. For example, let's say that our feature are just word counts. How often Viagra, meeting and free, etc. Why Viagra? Alright, meeting and free. Are you free to meeting? And generative model view. Alright, what is generative? It says how emails are written. Model how emails are generated for each class. What do we model? We model the join the p of x given y, p of y given probability. Meaning, first sample the label y, spam not spam. Oh, okay, y is the classification, spam not spam. And then say probability of getting these x features, words from this. If the feature gets given the label, so learn probability of y spam given not spam, probability of x, and look like for the x given y not spam. You can, once that we have this joint probability distribution or each of its marginals and conditionals, we can say what is probability of spam. Okay. Naive Bayes. Assume word appearances are independent given the class. Each word follows a class subspecific either nodally or multinomial. This form says okay. Discriminative model says what is the difference? What is the threshold? Okay, directly model. I think it is more about what is the decision metric. Directly model the boundary between spam and not spam. What do we model? Probability of y given x. So in generative, we used to compute estimate those other parameters, compute p of y given x. Now we go straight for p of y given x. We do not care how emails are generated. We just care about which label fits best. The features, no modeling p of x given y, no assumption about email generation. P of y given, this is it, we learn weights w, and that makes it. So yeah, let's go with the email example. Alright, email get free Viagra now. Alright, email is this, and then features one is Viagra. I didn't expect ChatGPT to give me this example. I'm shocked. Viagra is one, free one, now is. What if your child is using ChatGPT? Viagra is one, free is one now. Wait, that's a good question. Do they have a kid version of ChatGPT? Viagra is one, free is one, now is one, and all other words are zero. What is it? Okay, yeah, features exit. Generative model view, it says spam emails often contain Viagra and free. Non-spam email almost never use those words. So spam me. For the x given spam is Discriminative model says Viagra and free are strong features that separate spam from all. These are the words. Assign them large positive weights in W if those words are present. How do you find those though? It only cares about the decision rules, not how things are made. Which one is better? So which one is better? So generative model gives me a more causal way of looking. Causality. Actually, these are not our questions, these are just curious. It depends on what you care about. Situation, you only care about the prediction accuracy, discriminative is usually. You want to model how data is generated, generative is needed. You have missing labels or semi-supervised data, generative is often better. You want simple, fast models, generative can be simpler. You have tons of labeled data, discriminative wins. You have limited data and strong assumptions, generative can. Interesting. Discriminative models like logistic regression, SVM, deep nets usually achieve higher prediction accuracy when you have lots of labels, so for supervised. Generative models are often more sample efficient. They can start making reasonable guess with less data if their assumptions are close to right. Model have a causal view. Subtle here is the truth. Generative are not automatically causal models, but they are closer to causal things. I didn't mean the causal in the sense of causality and alright, that's good. I think we looked at it. Oh, we wanted to read the discussion. Let's go over the discussion and that's it. Dude, who could have thought? Like, they invent something for a reason, like ChatGPT, and then users use it as they wish. Like, they don't care. Like, I don't care how smart this or how powerful this tool is. I'm just copying my text from the paper to here so that it can read it for me. That's how selfish I am. It is mechanism design, and I think trying to design a truthful mechanism is also bullshit.
Here's the full text you asked me to repeat. We have described latent Dirichlet allocation, a flexible generative probabilistic model for collections of discrete data. LDA is based on a simple exchangeability assumption for the words and topics in a document. It is therefore realized by a straightforward application of De Finetti's representation theorem. We can view LDA as a dimensionality reduction technique in the spirit of LSI, but with proper underlying generative probabilistic semantics that makes sense for the type of data that it models. Exact inference is intractable for LDA, but any of a large suite of approximate inference algorithms can be used for inference and parameter estimation within the LDA framework. We have presented a simple, convexity-based variational approach for inference, showing that it yields a fast algorithm resulting in reasonable comparative performance in terms of test set likelihood. Other approaches that might be considered include Laplace approximation, higher order variational techniques, and Monte Carlo methods. In particular, Lysink and Kappan, 2002, have presented a general methodology for converting low-order variational lower bounds into higher-order variational bounds. It is also possible to achieve higher accuracy by dispensing with the requirement of maintaining a bound, and indeed Minka and Lafferty, 2002, have shown that improved inferential accuracy can be obtained for the LDA model via a higher-order variational technique known as expectation propagation. Finally, Griffiths and Stavers, 2002, have presented a Markov chain Monte Carlo algorithm for LDA. LDA is a simple model, and although we view it as a competitor to methods such as LSI and PLSI in the setting of dimensionality reduction for document collections and other discrete corpora, It is also intended to be illustrative of the way in which probabilistic models can be scaled up to provide useful inferential machinery in domains involving multiple levels of structure. Indeed, the principal advantages of generative models such as LDA include their modularity and their extensibility. As a probabilistic
Maybe we
module,
should go over
LDA can be readily embedded in a more complex model, a
more
property
recent
that is
paper
not
and
possessed
also
by
one
LSI.
review paper.
In recent work, we have used pairs of LDA modules to model relationships between images and their corresponding descriptive captions. Bly and Jordan, 2002. Moreover, there are numerous possible extensions of LDA. For example, LDA is readily extended to continuous data or other non-multinomial data. As is the case for other mixture models, including finite mixture models and hidden Markov models, the emission probability, PWN mid ZN, contributes only a likelihood value to the inference procedures for LDA, and other likelihoods are readily substituted in its place. In particular, it is straightforward to develop a continuous variant of LDA in which Gaussian observables are used in place of multinomials. Another simple extension of LDA comes from allowing mixtures of Dirichlet distributions in the place of the single Dirichlet of LDA. This allows a richer structure in the latent topic space, and in particular, allows a form of document clustering that is different from the clustering that is achieved via shared topics. Finally, a variety of extensions of LDA can be considered in which the distributions on the topic variables are elaborated. For example, we could arrange the topics in a time series, essentially relaxing the full exchangeability assumption to one of partial exchangeability. We could also consider partially exchangeable models in which we condition on exogenous variables. Thus, for example, the topic distribution could be conditioned on features such as paragraph or sentence, providing a more powerful text model that makes use of information obtained from a parser. Let me know if you also want me to summarize it or explain it line by line. This section is the real future work and philosophy part of the paper.
Topic modeling. A review of topic modeling methods 2020. That sounds nice. And we have another thing. Springer Open Smart Literature Review, a practical topic modeling approach. And NIH is at the top, a topic modeling comparison between LDA and NMF. Not a motherfucker. Select a number of labels of topics and just... Let's go Google Scholar, by the way. Okay, first one is again Elsevier. A review of topic modeling methods. Then we have the evolution of topic modeling, which is 2022. And is there a number of citations? Alright, they're good, like cited 781, the other one 252. The other one is topic since 2015, yeah, like let's 2025. Let's say since 2024. Ethical dimensions of generative AI across domain, machine learning, structural human centricity. Alright, anytime. overview of my tools. This is 2007. No, okay, so we want a 2020 and these two are enough. The evolution of topic modeling is interesting. Wow, that's crazy. You build a platform now that the future is all about data. Because Munzer said, and I agree with him, that if you got enough machine learning, you can algorithms are improved. Now what has value is your data. You build a platform, people go there, you record what people do, and you get a valuable data set. Then you sell it. That's the future. So PDF. And then I will say here. So latent Dirichlet, we already studied. Oh, I should close it first. Oh. No! Then a review of topic modeling methods. Let's get this paper too. Is it a book or is it a fucking paper? What are you talking about? No, it's a paper. I don't want to get it physically. What the fuck? No. What? Where can I see this paper? They have a journal pre-proof. I'm dead. Honestly, I'm dead. Fuck this, I'm so tired. So warm. Oof, oof. 5 minutes. 5 minutes and we are done. Ow, ow, ow! Let's go. So we got there. Alright, say perfecto. We got our papers and now it's time for counter. One thing before that though. So once we are done with topic modeling, which here I think is related to information retrieval and everything. Still I don't know what is the main problem. Like they are close problems, but they're not exactly the same. It's like okay, I got the main idea of there. It's very close. I say that like it's about the classifying. That's why they are close. But in this work, in LDA, I didn't see any effect of ranking, right? If you remember, they had the assumption of exchangeability. LDA, exchangeability, no effect of ranking. So it was kind of blind to grammar rules, how you say a sentence. It was just looking at words. That's I think what I. Anyways, good for right now. We will get back to it. And then what was it? Here. In that sense it is close, and we also have our R, which is close, so I don't think we can have the assumption of exchangeability in ranking, because ranking matters. Let's roll. Package is good. Who's this guy? Do you love that or no? Honestly. I mean, it's good. Oh, shit. Dude, leave it for me. Shoot you. shoot. Where are you guys? Nobody's going there. Ah, dude, I was so funny. Don't fucking move. Shit. Ow! This is a shit show. This is a shit show. This is a shit show. Oh, motherfuckers. You know where to look at. Oh, dude, that was. Alright, I'm not gonna move much. Where am I getting? Wait, where was it from? That motherfucker is cheating. He has some. Where is he? Oof. Yo 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 yo. There are. Omakase. Dude, how did he know? You know you're playing with pros. And there are no cons playing with the pros. There are no cons playing with the pros. Headshot. Except the way your life will be exposed. Like, are we clean? Where should you? In his jaw, honestly. I could. Oh, they had two boxes. Two boxes, bots. You know, cars that you're playing with the pros. I think he was cheating actually. Why is he dancing, by the way? I don't know. How can you dance? Oh, who was that? Semporo. We are almost there, guys. Don't worry. Oh, I can see something. Dude, we need to kill faster and sooner. shit. Natasha Shah. Natasha Shah. Kill him. Where was he looking at, by the way? Oof, that was quick and doorbell. 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 Oh shit, I missed it. Fuck this. This is gonna cost me big. Don't. I. Temporo. Oh shit, I thought there was somebody. No. God's plan. No, fucking. Oh, Centauri is actually number 4. It's getting big. I saw his brain explode. I saved him, honestly. I saved the hero. So I am a hero. Oof. This game is so quick and fast, and they're just shooting at us while running towards us. Dude. Who killed him? Not me? I did. Oof, I got my favorite gun, dude. Nobody can stop me. My boy is right there. Cover. That was so fucking stupid. What was I doing? Like, don't be so scary. Oof, what a headshot. Dude, that was a headshot, man. What's the hole over there? That I know. Ah, did they save? Motherfucker? Huh? Did they kill you or not? Jesus. Oof! Most awkward moment of his life. Planned all the way to hide there, and then me killing him like a whole. Oof. Not even touching my snipe. But these fuckers, they're so fucking good. It's fucking good. Feels so fucking good. Lulu. Motherfucker. My boys are killing me. How many more of you should I kill? Where was he? Fuck you! I want to kill Sempora. I don't. This game became so. It is not about game. It's not about having fun. This is fucking personal. Did you enjoy? Do you fucking enjoy me or no? Dude, who is it? Aromaki. Last one. All the headache is gone. Let's go. Ah, that was stupid dumb. Stupid dumb chick. He killed both of us? Oh, did you enjoy that shit or what? Yeah. I fucking two of them! You cannot focus on two things, guys. That's... Wow, wait. Wait, Semporo is kind of behind. Why is he so behind? What the fuck was that? Alright, chill, dude. Chill. You are not at their level, so... Oof. Nice job. Oof. Somebody knifes me from behind, I bet. Nobody shows up from there. It's just funny. Well, we need to get some forces from here, otherwise... Ooh, they are we so much better than them? Cardo is in San Diego, I know. He's in heaven, bro. Bro, leave some shit for me. I can hear. We are so good at this game. I mean, we, the rest of us. Alright, I'm gonna chill. The thing is that I chilled and nobody showed up, so... Oof, finally. Fucking Semporo. Woo-hoo-hoo! I think he was Semporo, wasn't he? Oof, I killed you so good. almost came. Ah, dude. Bishop of Wales. That's amazing. I love that. Dude, fucking ridiculous. Oh, I'm the last one. Shit, this sucks. I don't want to be the last one. Shit. Sopranos. What was that? No, Sempro. Semporo. Do not knife me, guys. Kill me, but do not knife me. I think he was about to knife me. This guy is dancing all the time. One more round of baggage, if it's possible, and then we are leaving. Screen time, guys. Screen time. We need to change these desktops. If we are looking at these screens forever, we need to come up with something. Maybe looking through this. Anyways. Okay, this time I'm gonna chill. Let Bishop of Wales. Let's hide somewhere and kill once in a while. That's the verdict with it. I think this game is very chaotic. Did you see that motherfucker? How could you? Shit. Easy, bro. Somebody hide. Oof. You see, I just try to help my friends. I'm not gonna get involved in this fucking war. It's a war, honestly. It's a war. My team is there. Shit. Yo, Abal Fazla Hussein. That was the most honest moment of you and I. They are fucking showing no mercy. Oof, dude. John. Oof. Come for me, motherfucker. Did you see that chill wipe, how amazing it works? Because now they are putting themselves at risk, so see, just what got a bit arrogant and they put me back. I'm just saving others. I've already saved. See, that's how I help. How I help the community. This war is already. Did you see that motherfucker? He came here and he decided to go back. What's going to happen? I didn't kill. Fuck. Oh shit, dude. Chill, bro. This is a real war, maybe. Oof. Amir, what are you doing, bro? Wait, I didn't kill? Where are you? Jesus. Bro, I'm with it. Shit. You see that? Oof, oof, oof. He's shooting. I didn't see. Dude, nobody knifed me. I will go somewhere that I can be shot clearly, but I'm not gonna. Swear to God, they're gonna knife me so bad. Who I killed? Who could have seen it? Let's go, donkeys. Three knifers. Someone kill this motherfucker. Ah, Ricardo is below me. Alright, that's it enough. Alright. Thanks, guys.